Hello guys, welcome to this conditional probability and independence video. Let me begin by giving you an example of what conditional probability is. So let's begin by imagining that we have a die, a balanced fair die. Sorry, this is kind of ugly. Let's define two events. Let's call A the event of observing a number 1, and let's define event B as the event of observing an odd number. So first of all, if we want to compute, let's say, the probability of A, since A is the event of observing a 1, then the probability of observing a 1 is just 1/6. Again, we are assuming that all outcomes are equally likely. But now let's repeat the experiment, and before watching the actual result, let's say that we have a piece of information. Let's say that we throw the die and we know, let's write it, we know that an odd number is in the upper face of the die. An odd number occurs. We have an odd number. So now, if we know that an odd number occurs, now what's going to be the probability of a 1 in this case, now that we have this new piece of information? Well, since we know that an odd number happened, then we can kind of define a new sample space that includes the odd numbers, which are 1 and 3 and 5. So this piece of information is going to give us a clue of how we can define a new sample space. So now, focusing only on this sample space, what is the probability of seeing a 1? Well, now in this case, after the information, after knowing that an odd number occurred, then the probability of seeing a 1 is just 1/3. So before having information, we had the intuition that the probability of observing a 1 was 1/6. But after having a piece of information, then we can adjust how we assign probabilities, and now we assign to the same event, after knowing this piece of information, twice as much as the original probability, right? So this is the idea behind conditional probability. Of course, we need a formal definition. So the formal definition is in the notes. You can find it there, and in the notes you will find the following formula: the probability of A given B. This is how we write conditional probability. This is just the probability of the intersection over the probability of the given event. Of course, the probability of B must be greater than 0. We cannot divide by 0. So again, how about if we solve the same exercise, but now using the actual definition? Well, we know that the event A was the event of observing a 1. We know that the event B is the event of observing an odd number. So the intersection between A and B is just A, right? The intersection between these two sets is just the number 1, which is just the set A. So the probability of the intersection is just the probability of A. And now we have everything that we need to compute the conditional probability. So let's do it. The probability of observing a 1 given that an odd number has occurred. This is just the probability of the intersection over the probability of the given event. This is just definition. But now we substitute the probability of the intersection with just the probability of A. The probability of A was just 1/6. So let me write 1/6. And the probability of B, let me write it over here, is just 1/2, right? Because the outcome of our die is either even or odd. So the probability of watching an odd number is just 1/2, and this is 2/6, and this is 1/3. So the probability of the conditional probability is 1/3, which is the same as our intuitive way of computing the conditional probability. So let me show you another example. Let me draw a table, something like this. Let me copy this line, add it here, and then here. Now let me see if I can, sorry, no. Now I need something like this. Let's copy this line. I'm trying to build a table, guys. Just bear with me. And this is the last one. Okay. Sorry, it's a little bit odd, but let me write a few things here. Let me write here an M that represents males. Let me write here an F that represents females. Let me write here the total. Now let me write here chocolate. Let me write here vanilla. Let me write here other. So let's say that we conduct a poll about the favorite ice cream flavor to some people, and you collect the following data. Let's say that the chocolate is the favorite ice cream flavor for 30 males, for 10 females, and of course if we add these two, it's 40. Let's say that vanilla is the favorite flavor for 12 males, for 32 females. So of course if we add this, we get 44. An other flavor, let's say 10, 6, of course 16. And if we add everything, we know that the poll was conducted to 100 people. So now, how about if I ask you for the probability of a person being male, given that his or her favorite flavor is chocolate? So with this kind of data representation, we can compute the exact same thing, right? Let's use the definition, which is just the probability of the intersection, M intersected with, let's call it just CH, over the probability of CH of chocolate. So let's compute this. So the probability of having chocolate as your favorite ice cream flavor is just taking all of the people who like chocolate and divide it by the total amount of people. This is just 4/10, or 0.4. Now for the intersection between males and chocolate. So now we look at the row of chocolate, the column of males, and we can see that the intersection is just 30. But we want to compute probabilities, so we need to do 30 over 100, which is just 0.3. So I believe we have everything that we need to compute this conditional probability. So this is 0.3 over 0.4. Let me take out my calculator. So now we divide 0.3 over 0.4. This is 0.75. So this is the conditional probability using the definition, but of course you can see that you can just take the information from the table to derive these probabilities. So it's not so hard. So this is everything about conditional probability. Now let me talk a little bit about independence of events. Independence. Well, two events are going to be independent if the occurrence of one event, let's call it event, does not affect the occurrence of another event. For example, this name of independent events is really close to our intuitive idea of independence. For example, let's imagine one event of smoking and another event which is getting lung cancer. So you would expect that the probability of developing cancer is less than the probability of developing cancer given that you are a smoker, right? So this event, the event of smoking, will most likely affect the probability of getting cancer. So this is an intuitive example of two dependent events. But another quick example of independent events may be the temperature of today and the temperature of 1 month ago. Well, the most likely thing 1 month ago is that this temperature has little effect on the temperature of today, or maybe the temperature of 2 months ago, or you got the idea. But of course we cannot work with intuitive concepts. We need a clear definition. So the way that we're going to define independence is that events A and B are independent if the probability of A given B is just the probability of A, or if the probability of B given A is just the probability of B, or if the probability of the intersection is the same as the product of the probabilities. So if any of these three things happen, then events are said to be independent. If you prove one of these conditions for a couple of events, then the other two must be true. Let's say that you choose the first equation to prove, and it's incorrect. It's not an equality. Then the other two are not going to be an equality. So they are like linked. If one is true, then the others must be true also. If one is false, the other two must be false also. So let's work again with some die example. Let's say that we have our die, and here's 1, 2, and 3, and so on. Let's define the event A as observing an even number as the outcome of the throw of the die, and event B as observing a number greater or equal than 3, let's say. So are these events independent? Independent. Well, we need to compute one of the 3 equations over here to see if they hold. So let's work with the first one, or the probability of A given B is the probability of A. This should happen if A and B are independent, right? If A and B independent. So let's work out the probability of A. The probability of A is watching an even number. It should be just 1/2. Again, because the outcome is either even or odd, and we have the same number of even outcomes as odd outcomes, so it's 1/2. What else do we need? We need the conditional probability, which is just the intersection over the probability of B. So the probability of B is observing a number greater or equal than 3. So that's the same as computing the probability of 3, 4, 5, and 6. So these are 4 numbers out of 6. So this is 4 over 6, which is 2 over 3. We need the probability of the intersection. Let me move this over here so I can work in the probability of the intersection. First of all, let us compute who is the intersection of A and B. This is the set of even numbers that are equal or greater than 3. So we have 4 and 6, right? So the probability of the intersection is just 2 out of 6, which is just 1 over 3. So now the conditional probability of A given B is going to be 1/3 over 2/3, and this is going to be 3 over 6, and this is just 1/2. So the conditional probability of A given B is 1/2. If A and B are independent, then that should be the same as the probability of A. The probability of A is 1/2. So yes, this holds true. Let me underline it. This is true. So A and B are independent. We can try another way of solving this. So A was the event of observing an even number. B was the event of the number greater or equal than 3. So we proved this, but it should be the same if we try to prove this, for example. Probability of A times probability of B. So we have the probability of the intersection, which is just over here. It's 1/3. So let me write this. 1 over 3. It's supposed to be the product of A and the product of the probability of A times the probability of B. We know that the probability of A is 1/2. The probability of B is 2/3. So 1/2 times 2/3. 1/2 times 2/3. This is just 1/3. So this is the same as this. So again, they are independent. That's what we expected. So that's how you work with independence problems, guys. So that's all, and see you later. Thank you.